Hello everybody, this is Dr. Christopher White, and today we're going to continue with the second half of Lecture 16. It's going to focus mostly on the Mesozoic development of North America with a special focus on the modern west coast. Alright, so let's get going. So what's happening in terms of Mesozoic tectonics? Well, the development of the Cordilleran mobile belt is a pretty complex story, so strap yourselves in. So the driving force was the eastward subduction of the oceanic Farallon plate under the North American plate. That's what drives most of what's going to happen in the Mesozoic. Now this results in the thickening of the continental crust along the west coast, the formation of an extensive accretionary wedge, the accretion of several island arcs, so several island arcs stick themselves onto the side of North America, the formation of an island arc related to subduction, and the emplacement of numerous felsic and intermediate plutons. So, until the Mesozoic, with the exception of the late Devonian to early Carboniferous antler orogeny, the west coast of Laurentia, now North America, was on the whole relatively passive. There was relatively little tectonism that occurred. Now, before we get on to the actual formation, of the Cordilleran Orageny, we're going to focus on one smaller orogeny that happened slightly earlier. So this is the Sonoma Orogeny. Now, in the late Permian, a subduction zone develops off the west coast of North America. So here's North America, and a subduction zone is going to form somewhere around here, give or take a bit, approximately in the position of modern California. So what's going to happen is the oceanic and continental crust that's sitting off the west coast of North America is going to start subducting in a westerly direction. So it's going to start subducting under the oceanic crust out here. And that's going to produce a volcanic island arc. So this seafloor here, this oceanic crust and continental crust here, is going to be subducting in this direction underneath a subduction, down the subduction zone that's situated approximately here. So the closure of this basin, this body of water right here, will produce a collision eventually between the continental crust over here and the island arc over here. And when that happens, what you're going to get is you're going to get large pieces of continental crust are going to start being pushed in an easterly direction, and you're going to get sheets of this continental crust pushed one on top of another, and that's going to produce a topographic high. So this diagram kind of summarizes what's going on slightly better. So so over here we have Laurentia. Over here we have the oceanic crust sitting off to the west of Laurentia, and this is a region that consisted of a mixture of oceanic crust with small pieces of continental crust mixed in. It was quite a mess really in this region. So this is the area that's going to be slowly subducted and that's going to produce eventually the Sonoma Orogeny. So this material that's in the basin here starts to be subducted down underneath this piece of oceanic crust here. Obviously the subduction of the oceanic crust leads to the melting of the oceanic crust through hydration melting, and obviously that produces magma that feeds volcanoes on the surface, producing a volcanic arc. Now eventually what's going to happen is as the oceanic crust in this basin gets subducted and destroyed, eventually one of these pieces of continental crust, or more than one, is going to actually hit the subduction zone. Now when that happens, I'm going to complete the wrong way there. When that happens, the continental crust is going to be thrust in an easterly direction. So you can see you get one sheet thrust east in an eastward direction, then another sheet over the top, then another sheet over the top, and then another sheet over the top of that. And so you've got layer after layer after layer of rock being thrust on top of each other. And as you can see, that thrusting produces a topographic high, which we can see is which we call the Sonoma Orogeny. So this sequence of rocks here consists of a mixture of basalt, which comes from the oceanic crust, felsic volcanics, which are related to the island arc here, and a mixture of limestone, sandstones, and mudstones, which are essentially basin sediments, the material that was on the seafloor and got scraped off as the oceanic crust subducted down into the mantle. And so all this material gets mashed together gets folded, gets rust, and it ends up producing this topographic high right here, which we refer to as the Sonoma orogeny. And so this area of topography is sometimes referred to as Sonomia. And so that's the Sonoma orogeny. It's a relatively straightforward one, nothing particularly spectacular going on, but it does mark essentially a stage of orogenic development of the west coast before the Cordilleran orogeny actually starts. So you can kind of see what's going on here. So these two pictures are going to show you pretty much what's happening. So here's our basin, here's our island arc, and this ocean floor here, this sea floor, and this continental crust material here is going to start subducting in a westerly direction. Now, obviously, the oceanic crust, when it goes down to the mantle, is going to melt, producing the island arc here. This material here is being subducted down until eventually, one of these pieces of continental crust hits this subduction zone. And obviously, when it hits that subduction zone, it's going to essentially gum up that subduction zone. It's going to stop it working effectively. And so the pressures produced by the fact that you've thrown a spanner in the works, essentially, it's not working correctly. Essentially, the buildup of stresses results in these very large thrust faults, which pushes rock to the east, and that ends up producing a landmass situated over here, which we refer to as Sonomia. Now, to be clear, there is a lot of uncertainty about the Sonoma orogeny. It's not very well defined at all. I mean, just to show you how poorly defined it is, geologists can't actually agree on whether the subduction that produced the Sonoma orogeny actually went to the east or went to the west. Now, I said it was going to the west, but there are some models that say nope, the oceanic crust was actually subducting to the east. And that's what produced the Sonoma orogeny. So there's a lot of debate about this particular orogeny. So, we're not going to go into it in particularly great detail because it's not particularly well defined. Right, so the Sonoma orogeny is sitting down here at the Permian-Triassic boundary. And so once the Sonoma orogeny is complete in the early Triassic, you're going to notice we have a period of passive conditions again. So from the middle Triassic all the way through to about the middle Jurassic, not much is really happening on the west coast. It's pretty quiet. So during the early Jurassic, we are going to form a steeply dipping subduction zone along the west coast. Now, the formation of this subduction zone is directly related to rifting along the east coast. So as the Rift Valley starts to open up over here, it's going to start pushing North America west in a westward direction. And so obviously, as North America moves in a westerly direction, it has to go over the top of the Farallon plate, which is a plate of oceanic crust, which is situated out here. Of course, there's me going the wrong way again. Okay, so the formation of this subduction zone, the steeply dipping subduction zone, was the result of the westward movement of North America over the Farallon plate as the Atlantic basin began to develop on what is now along the modern-day east coast. So this subduction zone controlled the Cordilleran Tectonics from the early to middle Jurassic all the way through to the Cenozoic, so for a period of somewhere in the region of about 140 million years. And it marks the beginning of the modern circum-Pacific orogenic systems. That's essentially the ring of volcanic activity that goes all the way from the southern tip of South America all the way around the Pacific to New Zealand. So the Cordilleran orogeny occurred between the middle Jurassic and the middle Paleogene. So remember, the Paleogene's in the Cenozoic. So it consists of a series of individual mountain building events that occurred in different portions of the Cordilleran mobile belt at different times. So the formation of what we would consider to be the Rocky Mountains is not a one-off event. It actually takes several steps to end up forming them. So there is often some degree of overlap between these different events. If we go back to the previous diagram, you can actually see how we have these three main orogenies: the Nevadian orogeny, the Sevier or Severe orogeny, and the Laramide orogeny. You'll see there's significant overlap between those orogenies. So, where are we? Sorry, I'm getting lost. I do apologize. So, most of the tectonism is related to North America's westward movement, which caused it to override the Farallon plate. So, the Nevadian orogeny was the first stage of the Cordilleran orogeny, and that began in approximately the late Jurassic and continued into the Cretaceous. So we had the subduction of the Farallon plate, and that obviously produced considerable volumes of granite due to crustal melting produced by magma, produced by the melting of mantle rocks. And obviously those granites intruded the crust, and they formed huge batholiths, very, very, areas of which we get numerous intrusions, all, intruding the same area of crust, building up to very, very large quantities of felsic and intermediate plutonic rocks. Okay, so what about the Nevada and Orageny? So we get this rifting beginning along what is now the modern day East Coast, and that obviously starts pushing North America in a westerly direction. So this obviously, if you're moving North America in a westerly direction because you're creating new crust off the East Coast, you obviously have to start destroying old crust off the West Coast to make room for it, to allow it to move. So this movement, as I say, was achieved by the formation of a subduction zone along the west coast of North America, which allowed the Farallon plate, which was oceanic crust, to subduct eastwards underneath North America. And this produced a mountain range that was very similar to the Rockies along the west coast of North America. And then within this mountain range we have additional mass being added due to the accretion of the odd island arc just sticking itself onto the side of North America, sediments being deposited, and obviously these very, very large granite and intermediate plutonic intrusives, intruding this mountain range, adding even more mass to it. So this is our situation in the late Triassic. So you can see in the late Triassic, things are on the whole relatively quiet. Now we know by now rifting has started to occur over here. So this area here is beginning to undergo extension, but at the moment there isn't too much of a westward push. We can see we have a small subduction zone here, but at the moment North America is still firmly attached to Gondwana. Now by the time we're into the early Jurassic, this rifting here has gotten more advanced and it's really starting to push North America in a westerly direction, at which point this subduction zone here begins to become better and better developed. So now North America is trying to move in a westerly direction, and obviously as it moves in the westerly direction, the continental crust of North America starts to override the oceanic crust of the Farallon plate. So as we move into the middle Jurassic, did I miss a slide there? Yes, I did. As you can see, so over time, this subduction zone becomes even more well developed. Okay, and you can see because we have the oceanic crust subducting eastwards underneath North America, as it's melting, it obviously, so as the oceanic crust descends, it reaches the magic 150 kilometer mark, at which point it loses water. That causes the mantle rocks to obviously melt due to hydration melting. That produces a basalt, that produces a mafic magma that rises up, gets stuck at the base of the continental crust, melts the continental crust, and that obviously leads to the formation of large quantities of felsic and intermediate magmas, and those intermediate and felsic magmas then rise to the surface and feed volcanoes. And we can begin to see the formation of volcanic islands essentially above this subduction zone being produced by the melting of the Farallon plate as it descends down into the mantle. So you can see these island arcs begin to become better and better developed. So in the early Jurassic, not really much going on there. By the time we're about 180 million years ago, these island arcs are becoming very well developed. By the time we're into the middle Jurassic, you can see we have a very extensive amount of volcanic arc activity. We also have lots of sediment being deposited due to the erosion of all these island arcs, and the deformation of the crust over here is also starting to produce topographic highs. So we have a three-prong attack essentially. We have volcanic island arcs combining with the general deformation of this area, causing the continental crust to thicken up. And on top of that, we then have the erosion of this thickened continental crust, producing very large quantities of sediments. And all those three combine to start forming a mountain range, start forming an orogeny. So by the time we're into the late Jurassic, you can see that we have a well-developed mobile belt here. So this is the Nevada and Orageny right here. You can see we still have our subduction zone, and of course by this point this subduction zone is also bringing into range several island arc chains, and those are going to adhere themselves onto the western side of North America, adding additional mass. Okay, so by the early Cretaceous, you can see these island arcs are steadily moving closer, and you can see by the early Cretaceous, the mobile belt here is getting more and more well developed. Okay, so the Nevada and orogeny essentially led to the subduction of the Farallon oceanic crust. Obviously, that melted. That led to the formation of large quantities of felsic and intermediate magma. That felsic and intermediate magma rose up through the crust to feed volcanoes on the surface. But of course, the vast majority of that magma was never actually erupted onto the surface of the Earth. Most of it got stuck in the crust, where it went to form intrusions. And if you remember, where you have regions where you have lots and lots of intrusions together, you lump all those intrusions and you refer to them simply as a batholith. So the Nevadian batholiths are separated into the Sierra Nevada, the Southern California, the Idaho, and the Coast Range batholiths. So here are the Coast Range batholiths running down here, Idaho batholiths here, Sierra Nevada batholiths here, and the Southern California batholiths here. And so those are all related to Nevadian plate tectonics. So this area here was being actively compressed, so it was undergoing compressive plate tectonics, which is going to cause the continental crust to buckle and fault and fold, and that's going to cause this area to thicken up. So that's going to be, the first part that starts the formation of a mountain range. Then within that mountain range, you're going to have lots and lots of volcanoes. They're also going to add mass to the mountain range, making it build higher and higher and higher as more and more volcanic material is deposited. We also have within the mountain range these very, very large felsic and intermediate magmas intruding the crust. They help to add extra mass to our mountain range. And then on top of that, we have this raised area of crust that's now going to undergo relatively rapid erosion, and that's going to mean sediments are going to be deposited along what is now the modern-day western coast. On top of that, we also then have a few island arcs come in from the west, and they also stick themselves onto the side of North America. So as you can see, it's a very complex situation in the Nevadian. So off the west coast here, we have the deposition of all these clastic sediments that are being produced by the erosion of the Nevadian orogenic highlands. But also we have sedimentary material that's being scraped off the Farallon plate as it subducts in an eastward direction underneath North America. So this material being scraped off the Farallon plate and the clastic material being deposited due to the erosion of the Nevadian orogenic mobile belt essentially produces two distinct bodies of sediments. One is called the Franciscan group and one is called the Great Valley group. So the Franciscan group is a maximum of about 7,000 meters thick. It's quite a significant layer of rock, and it consists of a chaotic mixture of rocks accumulated during the Late Triassic and Cretaceous. So the complex contains greywackies, siltstones, black shales, and cherts. So those are kind of marine sediments, probably continental marine sediments. Volcanic breccias, that's going to be related to island arc deposits, and pillowed basalts and blue schists, those are obviously related to oceanic crust. So we have a situation where we have a real mixture, a real mess of material all being mashed together. So what that suggests is we have a situation where we have continental shelf, continental slope, and deep sea marine environments all being brought together at a subduction zones trench. And obviously at the subduction zone trench, the sediments on top of the piece of subducting oceanic crust are being scraped off to form the accretionary wedge. And occasionally some of the oceanic crust will get scraped off as well, and that will also be incorporated into the accretionary wedge. So the Franciscan Complex and the Great Valley group that lies to the east of it are separated by a major thrust fault. So this is a general diagram of what we've got going on here. So here in grey we have the Farallon plate that's subducting down underneath the continental crust of the North American plate. So east is over here, west is over here. Now as the Farallon plate subducts down, all the sediment on top of it, or at least a significant portion of the sediment on top of it, gets scraped off. So the oceanic crust goes plunging down, but a lot of the sedimentary material on top of it gets scraped off and it gets incorporated into this area here. So this is the accretionary wedge. And this area here essentially is what we refer to as the Franciscan Complex. And so this is a mixture of marine sediments which were on top of the oceanic crust and got scraped off, little pieces of oceanic crust that get scraped off and incorporated into the Franciscan Complex, and clastic sedimentary material coming off North America and into the continental shelf environment. So you end up with, these environments all intersecting at the same place, producing a real mass of very badly deformed, very, very messed up sedimentary and occasionally volcanic rocks. So the Great Valley Group is located here. It's this kind of like pinky purple mass there, and that's located behind the Franciscan Complex. So the Franciscan Complex was the main focus of all this deformation. That's where pressures were going to be at their highest. The rocks here are going to be very strongly deformed. Then behind it we have the Great Valley Group. That's going to be a slightly lower pressure region, so they're maybe not going to be quite as badly deformed as the Franciscan Complex. So the Great Valley Group is extremely thick. It's 1,600, well, I'm saying 1,600, let's try that again. So 16,000 meters thick. And it's a mixture of conglomerates, sandstones, siltstones, and shales that were deposited into the continental shelf environment at the same time as the Franciscan Complex was forming at the trench. So the Franciscan Complex and the Great Valley Group are contemporaneous. They occur at the same time. So in terms of the Great Valley Group, well, the clastic sediments that are being deposited into this environment are coming from the erosion of the Nevadian highlands actually on continental North America. That's producing lots of sediment that's being dumped off the coast to form the Great Valley Group. So by the Late Cretaceous, most of the volcanic and plutonic activity started to migrate from an area started to migrate eastwards into Nevada and Idaho. So what we have is a situation where initially we start off with a rather steep subduction zone, and most of the volcanic activity is located very close to the trench. Now as we move into the Late Cretaceous, what we begin to see is this volcanic activity begins to shift further inland. So it moves essentially from an area that would be approximately the modern day eastern side of California, and it starts to shift and move into what is now modern day Nevada and Idaho. And this shift of the volcanism was probably caused by a decrease in the angle of subduction of the Farallon plate. And this resulted in the descending plate reaching its melting point further east. So this is our initial situation during the Nevadian. We have the Farallon plate here in green, subducting down underneath the North American plate. Obviously, as it subducts down, it reaches this magic 150 kilometer line. That's where the dehydration melting takes place, and that eventually leads to the formation of volcanoes on the surface directly above. Okay, so that's the basic model of subduction. So that makes perfect sense. So what seems to have happened is during the Cretaceous, the angle at which the Farallon plate is subducting decreases. So the angle of subduction becomes much shallower. And what this means is it takes much longer for the descending Farallon plate to actually make it to the magic 150 kilometer depth. Because if it's dipping steeply, the plate's going to drop down very, very quickly, and it's going to reach that 150 kilometer depth very, very soon. In contrast, if subduction is rather shallow, it's going to take much longer for the piece of oceanic crust to actually reach that 150 kilometer depth. So this means by the time it does actually reach the 150 kilometer depth, the oceanic crust is now a lot further under North America, and so when it does melt, producing magma that rises to the surface to form volcanoes, those volcanoes are going to be much further away from the trench. So over time we see volcanic activity shifts steadily inland, and we relate that to a shallowing in the angle of subduction of the Farallon plate. Okay, so we've been going for 25 minutes, so this is a good place to pause the presentation. So get up, have a walk around, go get a glass of water, and please come back in a couple of minutes. Okay, so the Nevadian orogeny was followed by the well, you can pronounce it one of two ways. You can call it either the severe orogeny or the severe orogeny, depending on how you want to say it. I personally prefer the severe orogeny. So the second stage of the Cordilleran Orageny affected North America from Alaska to Mexico. So this was a pretty extensive orogenic event. So the shallowing of the subduction angle meant that, number one, the stresses were no longer focused along the subduction front, but instead became spread out through a larger area of continental crust. And that also meant that the subducting slab spent more time grinding against the North American continental crust, so stresses were applied to areas of the crust that were previously unaffected by the Nevadian orogeny. And this caused the thrust faulting, which built up the Nevadian range closer to the trench to migrate eastwards along with the volcanism. So this diagram here gives you some idea of what's going on. Okay, so here's North America, and here is the Farallon Plate, and this is the Nevadian orogeny. So we can see the subducting oceanic crust is dropping down very steeply. Obviously that's melting very, very quickly because it's reaching that magic 150 kilometer depth relatively quickly because it's dropping so fast. It's melting, producing magma, rising to the surface that's feeding volcanoes. And these volcanoes are located relatively close to the subduction zone itself. So that's the Nevadian orogeny. Now, obviously, because the oceanic crust isn't in contact with the continental crust for that long because it's subducting so steeply, it means that most of these deformational forces, the compressional forces, are limited to this region right here by the subduction zones. This is going to be the area of highest pressure and greatest deformation. So this means that all the deformation and all the volcanism is located very, very close to the subduction zone. Now, as the angle of subduction shallows, part of the severe orogeny, well, we've already discussed that means that it takes longer for this oceanic crust to reach that magic 150 kilometer depth, and so that means it takes longer to melt, and so that means we have a shift of the volcanoes from this area here to more inland areas. So we see volcanism shifting and moving eastwards. Now, also what's going on is the oceanic crust is now going to spend more time in contact with the continental crust. So that means all the stresses, all those compressional forces that were once upon a time focused on this little area here, are now being spread out throughout a much larger volume of rock. And so that means that this area here, which was, at least initially, behind the Nevadian orogenic front, completely undeformed, all of a sudden begins to become exposed to tectonic stresses, and we start seeing the formation of folding and faulting, and especially we see the formation of lots and lots of thrust faults. And they're going to start pushing sheets of rock, one on top of another, on top of another. So that's the shift, that's the change we see as we go from the Nevadian to the severe orogeny. So we see both volcanism and tectonic deformation shifting in an easterly direction, and that appears to be related to a shallowing in the angle of subduction. So by the late Cretaceous, the thrusts associated with the severe orogeny had reached the Idaho-Washington border. So they were working, they're working their way quite a long way inland. And so as we can see in this diagram here, so we have this raised area here. So these are the highlands associated with the Nevadian orogeny. Okay, and the volcanic activity is slowly shifting its way eastwards. And we can also see here we have these thrusts where sheets of rock are being pushed upwards because of the tectonic stresses, and that's resulting in the formation of the Sevier thrust fold belt, which is sitting behind, well, in an area that was to the east of the original Nevadian orogenic belt. So these low angle thrusts push large blocks of rock, or especially Paleozoic sediments, over younger Mesozoic rocks. So we have Mesozoic sediments over here, and we're having sheets of Paleozoic rock being pushed over the top of them. So we have older material being pushed over the top of younger material. So thrusting is, of course, the result of crustal shortening. So what's happening is, because we have these two pieces of crust bang into each other, just like, you driving your car into another car, two cars going head on, obviously they're going to crash into each other, there's going to be deformation involved. So we have essentially the oceanic crust moving this way, the continental crust moving this way, and the collision between the two obviously imparts significant compressional forces, squishing forces, into this area of the continental crust. And so that's going to cause the continental crust to shorten. Okay, so a piece of continental crust that was initially 1 meter long is going to steadily get shorter, 99 centimeters, 98 centimeters, 97 centimeters, 96 centimeters, so on, as it's compressed. And in order to accommodate that compression, the continental crust can do one of two things. It can fold, which essentially implies it's deforming in a plastic fashion, so it flows. Or it can fail in a brittle fashion, and it can simply break. And when it breaks, that's when it's going to start forming joints and faults. And so the formation of these compressional forces and the formation of the faults produces these very low angle thrust faults, and that results in these sheets of Paleozoic rock being thrust over the top of younger Mesozoic sedimentary rock. So what you're going to notice as we go through these diagrams is you're not going to see the belt itself is going to stay relatively stable. Okay, so we're going to see we've got British Columbia here, then we're coming down into Washington State, Oregon, then into California here. Okay, and you'll see the belt itself doesn't really shift that much. What you're going to see is you're going to see the eastern side of the belt here is going to become more and more topographically strong. You're going to see more and more topography in this belt here as deformation shifts from this region closer to the subduction zone, and that deformation and volcanism starts to shift in an eastwards direction. So by the time you go from the 140 million years ago to just 130 million years ago, we can see that we've got more deformation beginning to creep in along this eastern margin here. You can see it's looking more and more topographically strong. We can see we've got more and more topography compared to this area here where the topography is relatively subdued. And then by the time we make it into the early Cretaceous, we can see we have very, very strong deformation along the eastern side of the orogenic belt. And so this is the result of the severe orogeny. This is the result of the stresses transferring from this region closer to the subduction zone, and these stresses being pushed eastwards towards, well, into what is now Alberta, Idaho, Nevada, that kind of area. So during the late Cretaceous and into the Paleogene, the final pulse of the Cordilleran Orageny occurred. So this final stage is referred to as the Laramide Orogeny. And the Laramide Orogeny occurred even further east than the Nevadian and the Sevier Orogeny. So we have this steady eastern movement of deformation associated with the subduction zone off the west coast of North America. And this is the result of a change in the angle of subduction of the Farallon plate from a descent of approximately 50 degrees to near horizontal. So by the time we're into the late Cretaceous, the angle of subduction for the Farallon plate has become nearly horizontal. So it's just grinding its way along the bottom of the North American plate. Now this is obviously going to spread the compressive forces caused by these two pieces of crust rubbing against each other over a very, very large area. So this decrease in angle caused a change in tectonism from high pressure thrusting, which makes up the Nevadian and Sevier orogenies. So that's lots of very tight folds, lots of faulting, lots of blocks of rock being pushed every which way. Instead, by the time we make it into the Laramide orogeny, we see that deformation related to the Laramide orogeny becomes a lot more gentle. We get crustal buckling. We get lots of very broad folds created, not tight folds, very broad open folds being formed. And we see a shift from thrust faulting to very, very steep faults. And these very, very steep faults push up large chunks of rock. So the large near vertical faults that we see are what we refer to as reverse faults. So a thrust fault essentially is quite a low angle fault, so that the fault's only going to be somewhere in the region of about 20 degrees. Not going to be very steep at all. And essentially older rock is going to be pushed over the top of younger rock in one of those thrust faults. Well, a reverse fault is the same thing. You still have older rock being pushed over the top of younger rock, but the reverse fault itself, this fault plane is considerably steeper. Okay, and so So what we're going to see is we're going to see blocks of rock essentially being pushed up over one another, but not in the same way as the earlier Nevadian and Sevier orogenies, where most of the faulting was thrust faulting. By the time we're into the Laramide orogeny, the faulting has shifted and it's more reverse faulting. And so what this reverse faulting does is it causes massive blocks of crustal rocks to be pushed upwards, otherwise called upthrown, producing a belt running through New Mexico, Colorado, and into Wyoming. So the majority of this orogeny occurs in the Cenozoic, so we're actually going to cover it in greater detail when we do the Cenozoic plate tectonics lecture. This diagram here is going to kind of summarize what's going on. So this is the initial situation. Initially we start off with very, very steep subduction. So the plate melts quickly as it subducts down into the mantle. That means the volcanoes are located relatively close to the subduction zone. And also because the plate drops off very, very quickly, it means most of the pressure is located in a relatively small area, and so we get lots and lots of deformation and volcanism relatively close to the subduction zone. Now, as the angular subduction shallows, we begin to see the point at which the subducting oceanic crust melts move eastwards, and so we see the volcanoes on the surface of the Earth also move eastwards. We see the Farallon plate spends more time in contact with the North American plate, and so that means the compressional forces get spread out over a larger area, and that means we see both volcanism and deformation shift eastward, so inland, and this results in the formation of the Sevier orogeny, the Sevier Mountains. Now, after that, we see that the Farallon plate begins to subduct at a near horizontal position, and so this means it spends a very, very long period of time rubbing against the bottom of the North American continental crust, and so this spreads the tectonic forces over a very large area, and that means deformation now moves even further eastwards, and that's going to result in the formation of these relatively steep reverse faults and very, very broad open folding. Okay, all the folding in this area here will have been relatively tight. We'll have lots of very, very steep, tight faults. Over here, on the other hand, we're going to get much more open folding, much more open deformation, because the tectonic forces are being spread over a much larger area, and so they're maybe not quite as concentrated and therefore not quite as strong. Now, just take a minute just to make sure you note the difference in angle when it comes to these faults here. These thrust faults are relatively low angle. These reverse faults are relatively steep in their angle. Okay, so do you know what? It's nearly been another 20 minutes, so let's take a break now. So let's pause the presentation, get up, have a walk around, go in a glass of water, and come back in a few minutes, please. Okay, everyone, so before we go any further, let's do the code word for this presentation. So the code word for this presentation is Paris. I repeat, Paris, as in the capital of the country of France. Okay, so let's move on and have a think about Mesozoic sedimentation. So the east coast and core of North America had a pretty consistent depositional regime throughout the Mesozoic. So they were dominated by terrestrial sedimentation. So you had floodplains, large rivers, depositing sediments onto those floodplains, and obviously you had areas where there was erosion, very similar to the modern type of environment that we have. So in terms of the sediments that were being deposited off the east coast, well, once rifting had finished, that the eastern margin of the North America became a passive continental margin, and essentially we just end up with the classic, the standard clastic sedimentary dominated system which we get off the coast on most passive continental margins. Lots of sandstones, lots of mudstones, and maybe some carbonates thrown in there as well. Now, in contrast, on the west coast, we had a mixture of volcanic deposits, passive marginal deposits, terrestrial deposits, and deposits related to shallow empiric seas. So it's, a bit of a mess. And of course, all of these were then deformed by these three very, very large orogenic events. So it gets really messy. So sedimentation along, by the way, that should actually say North America by now. along North America's western margin during the early Triassic was dominated by shallow marine sandstones, shales and limestones. So that's the classic passive continental margin sequence. So that shows us that during the from about the early to middle Triassic, the west coast of North America was passive. During the middle to late Triassic, the sea along the western margin regressed, exposing the shelf deposits to erosion, with terrestrial and marginal sedimentary deposits above them, particularly red beds. So what we see is above these continental shelf environments, we then see the deposition of a sequence of rocks related to fluvial systems, river systems, and desert systems. So what does the sedimentary sequence on the west coast tell us about the Mesozoic? Okay, so what we're going to do now is we're actually going to work our way through the sequence of rocks that we tend to see associated most strongly with the Mesozoic on the west coast. And we're actually going to analyze each one of these units, each one of these formations, to try and work out what was happening. Okay, so we're going to start with this simplistic diagram here, and then we're going to move to this very low resolution diagram here. Okay, so at the bottom of the sequence, so we have lower Triassic rocks. We have the Munkapai Formation. And that's a mixture of red and brown mudstones with mud cracks, ripple marks, fossil amphibians and reptiles, and their tracks. So that's essentially a fluvial system. It's a river system. So we also see thin beds of marine limestone, indicating that there were sporadic marine transgressions. So every once in a while the sea level would increase, the area would end up underwater, and during that time period we'd have relatively shallow warm seas, so you get little layers of limestone deposited. And there are also some evaporite beds within that formation, which indicates that there were also periods where the seas regressed, so the land became exposed again, and the conditions were rather dry, so even the fluvial system disappeared. So it would appear that during the lower Triassic, we had a situation where the coastline was relatively warm. For some periods of time, it was covered in rivers, so essentially it was a continental environment. For other periods of time, it was under very shallow seas, at which point we had, it was a carbonate shelf environment. And then for other periods of time, it was once again a continental environment, but it was very hot and very dry, so it was an arid environment. So it would appear the lower Triassic had quite a bit of environmental change. Now, by the time we move into the upper Triassic, we have the Shrinamump conglomerate, and that's an indicator of a period of erosion. So you can see we have the lower Triassic here, the upper Triassic here, and the middle Triassic is not there. So clearly that means it's been eroded away. We've lost it. So that means the contact between the lower Triassic here and the upper Triassic here is clearly an unconformity. And the Shrinamump conglomerate, which marks the base of the upper Triassic here, well, that's made up of rocks from the middle Triassic that were eroded. So what we see is the Shrinamump conglomerate. It's widespread. It unconformably overlies the Munkapai Formation, which is below it. And this indicates a period of erosion. Obviously, as I said, the middle Triassic is gone. So above the Shrinamump Formation, we have the Chiln Formation. And that's a mixture of shales, siltstones, and sandstones. It contains petrified wood, amphibian, very early crocodile-like creatures, and small dinosaur footprints. So this is interpreted as a dominantly fluvial system, so it's mostly a floodplain system, with occasional periods of drying out, producing a desert environment and an aeolian deposit. So once again, we have a period of change. So far we've gone from the fluvial semi-desert to very shallow marine systems of the Munkapai. Moved into the Shrinamump conglomerate. Essentially, that's the result of exposure during the lower portion of the upper Triassic. Then we move into the Chiln Formation, and this is a period where we have the area being cut by very large rivers with very big floodplains, and occasionally the area would dry out, leading to the deposition of arid or semi-arid deposits, mostly sandstones. So as we move from the Chiln Formation, we then move into the Wingate Sandstone, which is this yellow layer here. And so the Wingate sandstone is a clean, well-sorted sandstone with big meter-scale crossbeds. So that's a classic desert deposit. So by the time we've made it into the lower Jurassic, we now know we're in a desert system. So the west coast is a hot, dry, arid environment. Okay, so that's going to keep going. So then as we leave the Wingate, we move into the Chienta Formation. And that's a mixture of sandstone, shales, and limestones. They contain ripple marks and crossbeds. The sandstone beds contain well-sorted quartz sands, and the formation represents essentially a system of essentially a fluvial system, reworking desert sediment. So that's where these well-sorted sandstones come from. We obviously also have the sandstone, shales, and limestones. Well, that's a classic passive continental marine sequence. So what we have here is we have a situation where we have large rivers reworking earlier sandstone deposits. So these large rivers were reworking the Wingate sandstone. They were eroding it and transporting that, producing a sediment that was being transported around. And so the area was at times covered in large rivers, and at some periods of time it was underwater. And when it was underwater, it was essentially a passive continental margin within which we have the classic sandstone, shale, limestone sequence of rocks being deposited. So as we move out of the Chienta Formation, we then move into the Mona Formation, and this is red siltstones and sandstones, displaying ripple marks, crossbeds, and dinosaur tracks. So that's a mixture of fluvial and desert environment. So once again, we're back above sea level, so it's exposed. We're in a continental environment, and so we have a mixture of essentially river systems, and occasionally the area became drier, leading to it becoming covered in desert. So that's what's going on during the lower Jurassic. As we move above that layer, we move into the Navajo sandstone. Navajo sandstone is like the Wingate sandstone, so it's well sorted, quartz rich, meter scale crossbeds, contains dinosaur and crocodile fossils. So we're in a desert environment. So obviously that explains the crossbeds, the lots of sand. Obviously it helps to explain the dinosaurs as well. Dinosaurs by their nature tended to like warm, dry conditions. So that makes sense. Now, the fact we have crocodiles, on the other hand, that does tell us something, though. It tells us that clearly there has to have been some water around. So it would seem that what we had was a situation where we had a dominantly desert environment, but within that desert environment we had persistent bodies of water. Could have been oases, or possibly could have been large rivers. So as we move out of the Navajo sandstone, we move into the Sundance Formation. So the Sundance Formation is a mixture of limestones and poorly sorted sandstones with minor shales. So essentially this is a sequence of relatively shallow marine clastic sediments. So we're looking at a passive continental margin sediment here. So as I said, it's made up of shallow marine carbonates. So they have been these rocks were being deposited in the Sundance Sea. So the sandstones are produced by the erosion of the proximal highlands related to the Nevadian and Sevier orogenies. So those highlands are being eroded, producing lots of clastic sediments that are entering the Sundance Sea. Now, those areas of the Sundance Sea that have slightly less clastic sediment will have better water quality, clearer water, and so those areas will tend to be dominated by limestones. Okay, so then we move up into the Morrison Formation up here. Well, the Morrison Formation is a mixture of sandstones, mudstones, shales, and rare conglomerates. And this sequence of clastic sediments is the result of the Nevadian orogeny producing the Nevadian orogeny producing this very large mountain chain. And obviously this mountain chain was being eroded, and some of the sediments being produced by that erosion were being deposited along the eastern side of the Nevadian mobile belt, and that eastern side of the Nevadian mobile belt essentially is where the Sundance Sea was located. So the Morrison Formation essentially is a mixture of fluvial systems with seasonally arid environments. So once again, we're back above sea level. We have a highland area that's being eroded. Some of those sediments are being deposited along the eastern flank of this highland area. And this eastern flank is a mixture of, once again, fluvial systems, which occasionally become relatively arid, so relatively dry desert, semi-desert environments. So as you move into the lower and middle Cretaceous, we then have a sequence of sedimentary rocks. So you can see we have here we have sandstones, shales, and we also have a few carbonates mixed in there as well. So during the early Cretaceous, we have a marine transgression, which migrated south from the Arctic, and that produced the Murray Sea. And this transgression continued into the middle Cretaceous. At the same time, we had the eroding highlands produced by the Nevadian and Sevier orogenies, and that created a substantial clastic wedge. So all of this clastic material being eroded from the highlands was being dumped into the Murray Sea, and there was so much of it being deposited that it was actually causing the bottom of the Murray Sea to actually deform and warp. So as more sediment entered the basin, it put more weight on the floor of the Murray Sea, and it actually pushed it down even further. Obviously, when it pushes it down further, that means there's more room for more sediment. So then more sediment gets deposited into the space created, which then means there's even more weight pushing down, so the bottom of the Murray Sea gets even deeper. And so essentially what you end up doing is you end up forming a clastic wedge. So you had this big, thick sequence of sediments right next to the Nevadian and Sevier highlands, and this sequence begins to thin as you move to the east, as you move further away from the highlands. So the eroding highlands produced by the Nevadian and Sevier orogenies created a substantial clastic wedge containing sandstones, mudstones, and conglomerates. The wedge thinned to the east, where detrital sediments were not deposited. Carbonate sediments were dominant. So there were some areas, especially towards the east of this clastic wedge, where the amount of clastic sediments in the water dropped quite low, which meant better water quality, which meant you had carbonates being deposited. So within this sequence, we have substantial quantities of muds being deposited, and this obviously led to the formation of shale units. So at the time when these shale units were being deposited, it just so happened that the Murray Sea was actually a nice warm body of water, and so that meant it was absolutely stuffed with life. And so what happened is a lot of this life would obviously die, and so the carcasses would obviously sink to the seafloor, where they would become incorporated into the muds. That's especially true of photosynthesizing algae, which would have been there in their billions. Obviously, every day, thousands of them would have died, and they would have, the dead bodies would have sunk down to the seafloor, and they would have become incorporated into the muddy sediments. And so that means that as part of, during this time frame, we get quite a few layers of black shale forming. If you remember, these are these very organic, rich mud units that have a very black color to them. And they tend to form in relatively anoxic conditions, oxygen-poor conditions. So that would suggest that for periods of time during the Cretaceous, the water at the bottom of the Murray Sea actually became anoxic, it became oxygen-poor. Now eventually, by the time we make it into the Upper Cretaceous, the Murray Sea joined with a marine transgression from the south. So that marine transgression started in the Gulf region and started working its way north. Eventually it met the Murray Sea, and when the two bodies of water join together, we have the Cretaceous Interior Seaway. And so the Cretaceous Interior Seaway extends all the way from the Gulf of Mexico all the way up to the Arctic Ocean. So it had a maximum width of around 1,500 kilometers, and it divided North America into two, essentially. On the western side, you had the Rockies, and on the eastern side, you had the center and eastern portion of North America. So the eastern margin of the seaway received relatively little detrital sediment, and so it was dominated by carbonates. The western margin, closest to the highlands created by the Nevadian and Sevier orogenies, obviously received substantial quantities of clastic sediment produced by the erosion of those highlands. And so what we see when we look at the sequences, we see lots and lots of very coarse, relatively angular, moderately poorly sorted clastic sediments coming off the highlands. And we see that the position of the clastic facies associated with the erosion of these highlands changes. So we'll see in some occasions the conglomerate facies will move east or west depending on whether the depending on whether the highlands are being pushed up or whether they're just being eroded down. So this is kind of a very crude cross section through the clastic wedge associated with the Cretaceous Interior Seaway. So the basic situation is on this side we have the west, and this is where we have the Sevier and Nevadian orogeny. So we have high ground over here, which is being actively eroded, producing huge quantities of clastic sediments. And these clastic sediments are being deposited into the Cretaceous interior seaway. So this area here essentially represents water, the interior seaway. And as you can see, as we head from west to east, you can see we have a change in the units that we have. So we start off with these units here. So these are a mixture of sandstones and conglomerates. As we head this way, we head into more sandstones. And as we keep going, we head into mudstones. Then eventually, if we keep going all the way over here, we eventually grade into limestones. So I think that gives you, an obvious idea of what's going on. So we have the coarsest material closest to the highlands. Steadily, as we move this way, the material is getting finer. So we then have, we have coarse sands and conglomerates on this side, grading into medium and fine sandstones here, grading into silt and mudstones over here. So it's exactly what you would expect. When the rivers that are depositing the sediment drops it, obviously heaviest sediment deposited first, then medium sediment, and then finest sediment deposited last. The finest sediment will obviously be deposited at the greatest distance from the source of the sediment. So the sediments change from conglomerates and coarse sandstones, which are adjacent to the mountain belt, and they grade into finer sandstones and siltstones and mudstones as we move east. So the detrital sequence terminates and transitions into shallow marine limestones and chalks. They represent essentially the east coast of the Cretaceous interior seaway. So you'll notice that these regions, these areas, actually shift. We don't have a nice continuous boundary. You'll notice that they have this sawtooth pattern, this intertonguing pattern. You'll see that, for instance, this sandstone unit comes out, comes back in, comes out, back in, out, back in, and then you can see out again, in again, out again. So what you can see is that the regions are shifting. So why are they shifting? Well, the reason is during periods of active mountain building, when the highlands were being pushed up, when they're being pushed upwards, that means the rate of erosion will increase. So as the mountain range gets pushed up, the rate of erosion increases. That means more clastic sediment is being formed, and so that means that these facies will push to the east. So during periods of uplift, we see the conglomerate and sandstone facies pushes eastwards. We see the sandstone facies push eastwards, and we'll see the mudstone facies push eastwards. Now, in periods where the mountain building slows down, we will then see these facies move back to the west. So, for instance, when during periods of lower rates of mountain building, we see the conglomerate facies retreating towards the sediment source. Same thing happens with the sandstones. Same thing happens with the mudstones. So the shifts in these facies is the result of how quickly the Sevier and Nevada and orogenic belts are being pushed up. What rate of mountain building is occurring. So as the Cretaceous draws to a close, the Cretaceous interior seaway retreats to the north and south, and this passive marine basin transitions into terrestrial deposits, and then obviously as the sea is moving away, for a short period of time the area is relatively swampy, and so there's a window during which we have coal deposits being formed, and then eventually the area dries out completely, and then we have just the deposition of standard terrestrial sediments, mostly fluvial sediments and desert sediments over the top. So how important was accretion to the growth of the west coast? Well, much of the material that was added to the west coast of North America during the Cordilleran Orageny were detrital sediments deposited on the continental shelf, and these detrital sediments were sourced from the erosion of older continental crust that was being pushed up as part of the Nevadian, Sevier, and Laramide orogenies. So the vast majority of the material that's being deposited on the west coast actually came from the erosion of rocks that were part of the North American continental crust. Now, additional volume was added by the intrusion of the crust by felsic and intermediate magmas, producing very, very large intrusions. So that's obviously related to subduction. So that helps to add extra mass. And obviously there was additional material being added in the form of volcanic eruptions. So you had lava flows and pyroclastic material. Now, when we actually analyse the mountain systems associated with the Nevadian, Sevier and Laramide orogenies, we see that there are actually areas of them that are not only made from accreted sediments and rocks and plutonics, but there are also small lithospheric crustal blocks. So the vast majority of the mountain system is made of the stuff that we expect to see. It's made of, sediments. It's made of, sedimentary rocks that have stuck onto the side. It's made of sedimentary rocks that have been formed by the erosion of the Laramide, the Nevada and the Sevier orogenies, the mountain belts that were formed by them, should I say. And it also contains rocks that are essentially related to the volcanism associated with the formation of that mountain range. So everything looks normal. But within that mountain sequence, there are also small blocks of crust that clearly formed elsewhere. They shouldn't be there. Oh, there you go. There's one of my dogs. So, right, sorry about that. Just had to pause the presentation for a second there to let my dog out. Okay, so, where were we? So, yeah, when we look at the highlands associated, the rock sequences associated with the Nevadian, Sevier and Laramide orogenies, we can see that most of it looks normal, and then we come across areas of continental crust that clearly did not form in the local vicinity, so they weren't part of the North American continental crust. They're from somewhere else. So these blocks of continental crust that clearly aren't related to North America are referred to as terranes. And they are distinct from the other rocks of the Cordilleran Mobile Belt because we can tell this because they have different fossils, they have different stratigraphy, they have different sequences of rocks, they have different structural trends, they've been deformed in different ways, and they have different paleomagnetic properties. So we can look at the paleomagnetism and we can work out where on the surface of the Earth they formed. So in many cases, the differences are so stark that it's been suggested these terranes actually could have moved relatively large distances before they collided with North America. So more than 25% of the Pacific coast, that's extending from Alaska all the way down to Baja California, consists of accreted terrain. So they make up a pretty substantial portion of the mobile belt. So the terrains consist of volcanic island arcs, ocean ridges, seamounts, volcanic plateaus, continental crust, and all this material essentially represents stuff that was scraped off the subducting Farallon plate as it subducted underneath North America. So it is estimated that greater than 100 different sized terrains have accreted to North America's western margin during the last 200 million years. And so if we look at this diagram here, you can see the terrains, or at least a selection of the terrains, are picked out in this brown colour. So this is all material that's stuck onto the side of the western side of North America during the Cordilleran Orageny. So the terrains, along with the felsic and intermediate intrusions, add volume to the North American content, rather than the sediments produced by the recycling of continental crust. They didn't really add volume; they were just, remobilizing material that was already there. Okay, so that's it for this presentation. It was a bit of a short one. So don't forget, the code word for this presentation is Paris. I repeat, Paris. So keep an eye out for the next presentation, because that's going to be on Mesozoic life. And of course, that's the one where we start talking about dinosaurs. So great fun there. Okay, take care everyone.